Now, before we move on to equilibrium reaction, let's have a word on what are non-equilibrium reactions and what causes them to be non-equilibrium. You know, for a non-equilibrium reaction, if you start with a stoichiometric amount of the starting material, then at the end of the reaction, you would not have any of the starting material left. It will all be products. And a good example or a close example of these non-equilibrium reactions might be the combustion of hydrogen in presence of oxygen or of methane in presence of oxygen. And by stoichiometric amount, I mean the ratio of the reactants is the same as the coefficient in the balanced equation. Now, why do reactions behave irreversibly? The reason is, I mean, not a reason, like an analogy would be, say for example, you have this jar that's set on the top of a stool, draining out its jar at the bottom of the stool, right? Now the liquid inside the top jar, you can think of them as reactant. And the transformation you're looking at is the draining of the reactant from the top jar to the bottom jar. Even when the last drop of liquid drops from this top jar to the bottom jar, it will still be lowering its potential energy. And therefore, there is always a lowering of potential energy when the liquid drops from here to here, and this process goes to completion. Similarly, in a non-equilibrium reaction, there is always a lowering of potential energy when you go from starting material to product. However, non-equilibrium reactions are not the norm. They're actually exceptions. In fact, non-equilibrium reactions do not really exist, as such, okay? Like ideal non-equilibrium reactions. But to see an equilibrium reaction, your system has to be closed. If your system is open, your molecules will fly out. So every system we're going to see from here on are closed systems. So what happens in these equilibrium reactions? Let's say I have hydrogen and iodine in this closed container, okay, with this lid on top. And if I set up the reaction and I leave and I come back, say after 10 years, 20 years, or maybe even infinite amount of time, I will see in the reaction medium the starting material and the product existing at the same time together, even when you start off with the stoichiometric amount of the starting materials. We have seen about non-equilibrium reactions. So what makes these reactions reach equilibrium? Once again, an analogy would be, say you start off with these two jars, okay? Once again, the system is closed, and the reactant will flow, and this liquid on the left, I call the reactant. So initially, at time 0, you start off with all reactants. You turn the stopcock, which is symbolical of putting in the reaction conditions, and the reactants start gushing in to give you the product. Okay, they're moving in to give you product at intermediate time. When you come back later at the equilibrium, what happens is the reactants and products in this liquid analogy will have the same height. That means in terms of chemistry, when you reach equilibrium, the reactants and products will reach the same chemical potential. We'll not deal with what chemical potential is, okay? But just know that this is what causes equilibrium to be established. So what happens at chemical equilibrium? Chemical equilibrium is dynamic. What does that mean? Say, for example, the reaction we just looked at, the hydrogen plus iodine giving you HI, hydroiodic acid. You know the rate of forward reaction from chemical kinetics is given by the forward reaction rate constant, which is Kf, times the concentration of hydrogen times the concentration of iodine. And the rate of backward reaction is given by the backward reaction rate constant times the concentration of the product squared, and the squared term because there's a coefficient 2 in front of each other. At equilibrium, this reaction, the forward reaction, keeps going until it reaches equilibrium, where there's a critical concentration of the starting material and product such that the rate of forward reaction balances the rate of backward reaction. And notice the word balances. That means the reaction is still going. It will be wrong to say that at equilibrium, the reaction is stopped. That's wrong. At equilibrium, the forward reaction and the backward reaction happen at the same rate, such that the concentration of the species, that does not change. And therefore, in the previous example, when I drew equilibrium, I made these arrows the same size because I wanted to say that the forward reaction and the backward reaction happen at the same rate. So reaction is happening, but the concentration is not changing. And so then you can write down this rate expression, forward reaction rate equals backward reaction rate. And if you move things around a little bit, then at equilibrium, the rate, the concentration in the closed container, by the way, all these reactions are in closed containers. The equilibrium concentration of product over the equilibrium concentration of reactant, that is a constant number. And if you're using concentration in these values, then this constant number is called the equilibrium constant. And since concentration was used for calculating these are called Kc. And that also equals to the rate of forward reaction over the rate of the backward reaction. Now, what happens after you reach equilibrium, say like 100 years after equilibrium? The fun part is, equilibrium is, once it's reached, it's eternity, okay? The reaction will stay at equilibrium no matter how much longer you come back, okay? However, the important part we have to look at is what happens on the either side of equilibrium. That is, when you have excess reactant or you have excess product. If you have excess reactant, then you can tell that the forward reaction rate is going to be much larger than the backward reaction rate. So your reaction is basically moving forward, overcoming a small backward reaction rate from the product to the starting material. Okay? And that is given by this QC, which is called the reaction quotient, which is nothing but has the same expression as the equilibrium constant, except that these concentrations are not equilibrium concentrations. They are concentrations at a given time. So, if reactants are in excess, then H2 and I2, this bottom part of this expression is heavy, the top part is light. So, and since equilibrium is the goal of the reaction wants to reach equilibrium, to make QC equal Kc, the bottom will move, so the bottom will go lighter. That means reactants will go to product. Similarly, if your product is in excess, then your product, the backward reaction rate is much faster, and the reaction moves backwards. Or, seeing it from this QC point of view, the top of this expression is heavy, the bottom is light, so Hi converts to the H2 and I2, and the reaction goes backward. One analogy to remember what is going on is to think of the spring. At equilibrium, the block attached to the spring is, say, at this position. On the right is an increasing product, on the left is an increasing reactant concentration. So if you have an excess product, that can be thought of as stretching the spring and taking it to the right. So now, the spring, in order to reach equilibrium, will try to move this way, that is, in the direction of decreasing product. So your product will now convert to reactant. If you have excess reactant, that's like pushing the spring towards the wall over here. And now, the spring will want to go towards the equilibrium position, that is in the direction of decreasing reactant and increasing product. So the reactant will now go to the product. A simple example, or let's use the analogy. What happens if I start with excess HI? If I have excess HI in the closed container, then I have excess product and the spring is stretched. So when I release it, it tries to come to the center, and in doing so, the product converts to starting material. What if I add excess hydrogen at equilibrium? That means I am in principle pushing the spring towards the wall. And therefore, when I release it, the reactant will convert to starting material to product. This observation is summarized by the Le Chatelier principle, which states that if stress is induced in a reaction, the reaction will move in a direction to remove that stress. And by stress, we not only mean reactant and product concentration, but also heat. For example, if nitrogen and hydrogen react to give ammonia and heat, this classical Haber synthesis, if I add heat, additional heat to the reaction will go backward so as to consume the heat. If I take heat out of the reaction will move forward to compensate the heat that I've taken. So, we have looked at the fact that the closed system is needed for equilibrium to be established. Chemical equilibrium is dynamic. We have looked at the Le Chatelier principle.